Okay, hello grade 10s, welcome back. This is our second part of our first lesson on light, and we're now going to move into looking at a mirror. Okay, so now we're going to look at that light that travels in a straight line and what happens when it hits a mirror and bounces back. We call that reflection, but of course you know that. Okay, so what are these properties of light when light hits what we call a plane mirror? The word plane, P-L-A-N-E, simply means a flat mirror. Okay, so here's an example of a flat mirror right here. All right, this is what we're talking about, and because the mirror is flat, we can predict, based on something called the ray rules, what the angles are going to be when things bounce off a mirror. You know that when you look at yourself in a mirror, okay, you don't look distorted. The image that you see doesn't have anything wonky to it. That is very different from when you're looking at a mirror that has some curvature to it. So today we'll start with what happens when you've just got a plain mirror, and then the next lesson is, well, what happens now if it hits a curved mirror, if it's curved this way concave or this way convex. And you may have seen this before. Well, you've got wonky mirrors like this even in your car. On the side view mirror is a little bit different. Maybe you have a makeup mirror at home, a mirror that you've seen at the convenience store in the top left corner, right? They use it for catching shoplifters and just seeing what's going on inside the store. We can make use of these curved mirrors, but today we're just going to start first of all by looking at what happens when light hits a plain flat mirror. Okay, here we go. A laser beam clearly shows that light travels in a blank blank. Straight line. Good. Okay. The fundamental property of light, by the fact that it travels in a straight line, is used to understand how light behaves when it strikes a mirror or a lens. And these properties are the foundation of science. This is what geometric optics is. The characteristic and properties of light can be manipulated with mirrors and lenses for a range of uses that society has benefited from. You obviously understand some of the benefits of lenses because perhaps maybe you wear contact lenses, or definitely you know somebody that does wear glasses. Well, the lenses in a glass do something to distort the light as well, don't they? Okay, they change where the focal point of the image is in your eye so that your brain reads it as an image that is crisp and clear. Well, we can figure out where images are when we use mirrors as well. Okay, so most mirrors consist of two parts. There's a sheet of glass, okay, which is the front part, and then there's a thin layer of reflective silver that's at the back. Okay, if you've ever had an old mirror, you can even take this mirror and scratch it. We don't want you to do that, obviously, because we want it to be work. But this is the silver plate at the back of the mirror, and honestly, it can just peel off as well. It could be aluminum, right? If it's a cheaper mirror, you can just peel it right back off. So the mirrors you have in your locker, perhaps, that's exactly what they will be. Let's look at what these images look like, because in physics, we get to draw things, right? And we want to draw things based on what they actually like. So here we go. If this on the left-hand side is your actual mirror, where you've got the glass and then you've got your reflective surface, or the reflective thin film, what I want you to show is that when you draw a mirror, the reflective surface is going to be the straight line that you draw. The hashes at the back of it, that refers to the back of the mirror. Okay, so anytime you're drawing a plane mirror, which means a flat mirror, you're going to make sure that the reflective surface is the one that's the straight line, and then you're going to draw little hashes on the back. That's going to represent the back of the mirror. Okay, so if the light is traveling towards the mirror, well, then you're going to show a beam of light going like this towards the reflective surface. So that's something to take note of, because that's why, again, you've got your ruler, you've got your protractor, and you're sort of ready to go to be able to draw physics diagrams. So here we go. A plain flat mirror is going to illustrate how predictable this path of light is when it hits a mirror. Now, if we were in the lab, we would do this. We would set up the mirror on a sheet of paper. Okay, we just set it down. We would use our ray box, and this is what I got out last time. I'll just show you how it would work. Maybe I'll turn the light off next time and I'll do my little video and see if you can see it. Okay, I would take this ray box. I'm going to put the little mask at the front of it. So I just slide it in the slots like this, because I want the bottom to have only one beam of light coming through. I would lay it flat on the desk. I'd set my mirror up, Okay, and then I'm all ready to go. So you can see that I've got a mirror here shown using the physics way that I've just done it. That's my mirror. A couple of things on this diagram to note. Can you see which angle or which beam of light is the one that's going towards the mirror? Can you look and see that there are arrowheads? Okay, you're going to do the same thing. You want to try not to draw the arrowhead right at the mirror because then it kind of gets in the way of when you use your protractor, because you're actually going to set the protractor right down on your piece of paper and you're going to be measuring some angles, okay? There are some terms. The first one is the ray that goes towards the mirror is called the incident ray. Okay, that's the word you need to use to describe that. It's got an arrowhead on it, it's going towards the mirror. The reflective ray is obviously the ray of light that comes straight off the mirror as it reflects. So that's this line on the diagram right here. And this is called the reflected ray. Okay, so the incident ray is the ray of light, the beam of light going towards the mirror always, and the reflected ray is the ray of light coming away from the mirror. There's a law, the law of reflection. Okay, I want you to have a look at some of these angles that are going to be on here. First of all, you notice that there's like a little dot, 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 dot line that you would have used when you take a ruler and just put it at a 90-degree angle towards the mirror. What does that look like? It looks like this. The line coming straight off at an angle of 90 degrees from the mirror. This is called the normal. Okay, and your normal is the point at which your incident ray hits the plain flat mirror, okay? Where it reflects off of, right? The angle between the mirror and the normal is 90 degrees. So the normal isn't anything, like it's an imaginary dotted line that you just simply use your protractor, measure 90 degrees, and take your ruler and draw a straight line from the mirror. Because it's a plane mirror, the angle at which the incident ray hits the mirror and bounces or reflects off the mirror will be at the exact same angle as the angle it took between the incident ray and what we call that imaginary normal. Okay, let's look in the diagram and then I want you to label what it says. So the angle between the incident ray and the normal is called the angle of incidence. And this is a theta I, incident angle, the angle of incidence, okay? Again, it's the angle between the incident ray and the normal. And then can you see that the angle between the reflected ray and the normal, that's this one right here, is called theta R, and that's the angle of reflection. It is the angle between the reflected ray and the normal. So I want you to take this little section of your note, make sure you can label all of the points, and then pause the video, make sure you've got that note copied. Move on to the next part, and I'm going to show you what it would look like in the lab. All right, if we were to investigate the properties of light using what we call the ray mirror, can you see in the diagram right here? All right, I would set my mirror up on my piece of paper, and if you actually have a flat mirror at home, you're lucky. You could find any kind of flat mirror that you have. You could use anything you've got that will shine a beam of light. You can use a little laser pointer if you have one. You could try a flashlight if you have a really dark room, but you could take the end of your flashlight and put a little strip like an open strip of paper on the outside part of the flashlight and create your own beam of light. This is what where should I set this there? Can you see that there? This is what the the slit mask looks like. And if you've got a teeny little beam of light, you too could do this experiment at home. Okay, so you can do this simply on your piece of paper if you can lay it down flat, and then draw with your pencil a little dotted line along the beam of light, and then where that light gets reflected, dot 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 with your pencil. Turn the lights on, turn your flashlight off, and then if you've got your mirror and your normal that you obviously created where it's a 90-degree angle from the piece of paper, you can investigate what happens when you change the angle of incident versus the angle of reflection, okay? Again, your light is pointed exactly at the normal. So in this little lab activity, I'm going to give you an angle of incidence. You're going to guess what the angle of reflection is, okay? What if I set up this experiment so that the angle of incidence is 45 degrees? Okay, so let's go back to the diagram. I'll show you what that would look like. That means that the angle of incidence is 45 degrees. How would you measure that and show that in the lab? You'd measure from your normal to the incident ray. That is your angle of incidence. Set that up to be 45 degrees. What do you think or predict the angle of reflection to be? Any guesses? 45 degrees. What if your angle of incidence is 10 degrees? You guessed it. The angle of reflection is also 10 degrees. So it just gives you a sense of, let's do it in the lab and practice, okay? Here's where you've got your diagram. Again, fully labeled. You can see they've drawn just a dotted line for a normal, measured at 90 degrees to the mirror, okay? There's your normal. You would add on some labels. You are labeling the incident ray, you're labeling the reflected ray, you're labeling the angle of incidence and the angle of reflection. And can you do a little bit of math, a few tricky questions to see if you understand this principle? This is the ray model, and this is using a flat mirror. We call that a plane mirror. Okay, a couple of things to go through for here. Let you get caught up on a little bit of the work, and then we're going to move to the next lesson, which is just looking at how do you figure out where the image is going to be based on the mirror. Okay, and this is a little tricky because it's like you're going to look at a mirror and you can see yourself in the mirror. That is not an object, that is an image of an object. So what's the difference between it? And can you figure out some of the logistics as to how to describe that image? Okay, so that's what we're going to move on to next time. I'll catch you in a few minutes.